In this video, we're going to learn a couple new terms called altitude and median and how they apply to triangles. So let's go ahead and jump right in. We have these two new terms, altitude of a triangle and median of a triangle. So right off the bat, I just want to tell you what these are. The altitude of a triangle is a perpendicular segment that goes from a vertex of the triangle to the line that contains the opposite side from the vertex. So let's look at what that would mean in the two triangles that I have over here to the right. If I am looking at this vertex of this triangle and I wanted to draw the altitude of it, I need to make a segment that goes from here over to this opposite side and makes a right angle. So for instance, something that would not be an altitude would be a segment that does something like this. Because that segment is not going over and making a right angle here. It's making an acute angle and then an obtuse angle on the other side. So that's not going to be an altitude. What an altitude is going to be, what it would look like, is this segment that's going to kind of come straight down. Let me try that again. Let me try and get a little bit more on that vertex. It's going to come straight down here and make this right angle right here. Okay, so that would be an altitude of that triangle. Now the reason why it says to the line containing the opposite side, it doesn't say, you'll notice it doesn't say from the vertex to the opposite side. It has this little added phrase in here, to the line containing the opposite side. The reason that's in here is because of a triangle like this one, which you'll notice is an obtuse triangle. If I wanted to draw the altitude from this vertex, there's no way that I could go over to any place on this side of that triangle and be perpendicular, make a right angle. It's just not going to be possible, right? There's no place over here that I could draw a segment and make a right angle. So in that case, what we actually do is we temporarily extend that side. So we kind of pretend that that side keeps going over this way, right? This would be the line that contains this side of that triangle. And so now what we can do is we can drop an altitude that goes from that vertex and goes down and is perpendicular to that line that contains that opposite side. So that's what an altitude of a triangle is. Now, of course, you might be realizing that I could do that. I could draw that altitude from that corner. I could also draw an altitude from this corner, and I could also draw an altitude from this corner, right? I could draw an altitude from each corner of a triangle. So every triangle would have 3 altitudes, is another way of saying that. The next term is called the median of a triangle, and this one is a segment that connects a vertex to the midpoint of the opposite side. So for instance, let's say I wanted to connect this vertex right here to the midpoint of this side. Well, first let's kind of eyeball where we think that midpoint would be. Remember, the midpoint of a side is the midpoint of a segment would be dividing that segment into 2 equal parts. And so now my median would be that segment that connects those together. It's connecting the vertex here to this midpoint over here. All right? And every triangle, of course, would have 3 medians as well, because I could connect this vertex to this midpoint. I could connect the vertex here to the midpoint across the way over here. And I could connect the vertex here to the midpoint that's over here. So I can draw 3 medians for any triangle, just like I can draw 3 altitudes for any triangle. And that fact, the fact that there's 3 altitudes and 3 medians, is the basis of what we're going to take a look at next. So Theorem 5-7 is the next thing that we're going to take a look at. And we can kind of look at it 2 ways. We can look at this picture here, which is describing what's happening in this theorem. But I want to start by looking at just kind of the written description of what this theorem is telling us. So it says that the medians of a triangle will always meet at a point called the centroid. So in previous videos we looked at what happens when we drew the 3 perpendicular bisectors of a triangle and what happened when we drew the 3 angle bisectors of a triangle. And we realized that the 3 perpendicular bisectors met at a single point called the circumcenter. And we talked about how the 3 angle bisectors met at a single point called the incenter. Well, the same thing happens with medians. So if you look at this picture, segment CF is a median of this triangle because it's connecting a vertex to point F, and point F we can see is the midpoint of segment AB. So CF is a median. Segment AD is a median because it's doing the same thing, connecting A to point D, which is, we can see, the midpoint of segment BC. So AD is a median. And then BE is also a median. It's connecting B to point E, which is the midpoint of segment AC. We can see because of these marks right here. So we can see the three medians of this triangle, and they're all meeting at point G. So point G would be the centroid of this triangle. And that centroid has a special quality to it, which is that it's 2/3 of the way from a vertex to the opposite midpoint, or the midpoint of the opposite side. So point G is not halfway between A and D, right? It's not right in the middle halfway between A and D. It's a little more than half of the way. It's 2/3 of the way from A to D. So one way we can express that is we can say that from A to G is 2/3 of the distance from A to D. From B to G is 2/3 of the distance from B to E. And from C to G is 2/3 of the distance from C to F. Another way to think about that is that if I took one of these medians, let's say I took segment AD, which is one of the medians, and I divided it into 3 equal sized pieces, then from A to G would be 2 of those parts, and from G to D would be the other part, right? A to G, let's say if this entire median was 15 units long, then breaking it into 3 equal sized pieces would be like 3 pieces that are each 5 units long. Well, A to G would be 2 of those pieces. It'd be 10 units. And then G to D would be the third piece, or it'd be 5 units. All right, so that's what the centroid tells us. If we look over here at our diagram, and let's say we want to let's just first find the midpoints. Let's find the midpoints of all the sides of the triangle. Okay, so I'm going to find the midpoint of segment AC, the midpoint of segment BC, and the midpoint of segment AB. And then now what I'm going to do is I'm going to connect those midpoints to each opposite vertex. And you can see when I do that, they're all intersecting at this point that's called G right there. Right? So G would be our centroid. Actually, this looks a lot like what we have up here. Right? Now, if I measure the distance from G to D, let's measure that distance real quick, from G to D. So I'm going to grab my measurement tool here. It doesn't want me to do that. There we go. Okay, I'm going to measure the distance from G to D. And you can see that it says that it is 1.67 units. 1.67 units. So that is like 1/3. That 1.67 units is 1/3 of the distance from B to D. So if I measure now the distance from B to G, I'm expecting that to be 2 of those, 2 times as long. So let's just see if that's what happens. I'm going to measure the distance from B to G. B to G. And I can see it's 3.34, which is in fact 2 times 1.67. Now we can look at this another way. Let's look at the distance from C to G. So from C to G, it says it's 3.15. Now, from G to F should be half of that, because C to G, that's like 2 of the 1/3 parts of this median. From C to F, if we divide it into 3 parts, 3 equal sized parts, from C to G gets 2 of those. So C to G is 2 of the parts from C to F. G to F will be the last remaining part, so it should be half as long as what C to G is. Let's just see if that's what happens here. From G to F, 1.58, which probably because of rounding, it's a little bit, slightly more than half, but that's just because of the way the program is rounding. It's half of C to G. So that's theorem 5-7. It's really just in a nutshell telling us that when we draw all 3 medians of a triangle, they're going to meet at a single point called the centroid, and that centroid is 2/3 of the way from each vertex to the midpoint of the opposite side. So now let's take a look at one more theorem, theorem 5-8. And what this theorem is telling us is that the lines that contain the altitudes of a triangle will be concurrent. And we learned that that means that they're all going to intersect at a single point. You can see on this diagram, we're showing that we have triangle KLM, and then we have the three altitudes of that triangle. Remember, an altitude goes from a vertex and is perpendicular to the opposite side. And all three of those altitudes we can see are meeting at point X. Just real quick, let me show you that I can recreate what's happening here over here in my GeoGebra program. I got my triangle ABC, and so what I'm going to do next is I am going to create perpendicular segments going from each vertex to the opposite side. So there's a line that's perpendicular to segment BC, and it goes from A and it's perpendicular to segment BC, right? So there's one altitude of my triangle. My next altitude, I'm going to go from point B and be perpendicular to the opposite side. And then I'm going to go from point C and be perpendicular to the opposite side. And so you can see they're all intersecting here at point D, right there. So D, or in this case X over here, that's the point of concurrency for the altitude. It is called the orthocenter, right? So here's another new term for you. The orthocenter is the point of intersection, for the three altitudes of a triangle. They'll always meet at a single place, and that single place that they meet at is called the orthocenter. So in this picture here, that would be X, and in this picture over here, that would be D. And that's about all there is to know about theorem 5-8. The three altitudes, they meet at a single point called the orthocenter.